When I started my geology course at university many years ago, I learnt something extraordinary on the very first day. Most of the rocks we see around us started life as flat beds laid down at the bottom of the sea. I was shocked. So I put my hand up and asked the obvious question. If rocks started out as flat sheets, how come nearly all the rocks I see today are lumpy and knobbly? To which the lecturer replied, "Are you sure you wouldn't be more comfortable on an arts course?" But it was, I thought, a very good question. How do we get from this to this? And from this to this? Why are bits of trilobites, brachiopods and crinoids that lived at the bottom of the ocean now found on top of the Himalayas? And what the hell is going on here? In short, how did we make mountains out of sea mud? It took me 3 years to find out, but in this video I'll let you into the secret in just 23 minutes. By the end of the video, you'll be able to work it out for yourselves when you come across outcrops like these, so you can impress all your friends. Unless you've already got a geology degree, in which case you probably don't have any friends. Let's dispense with the rock that makes this kind of mountain first, because it's easy. It's a volcano. And no, you don't get any points for knowing that. This is made of another type of rock called igneous, which is molten rock that usually starts life in the hot zone of the Earth's mantle. Molten rock that pools below the surface cools quite slowly, and that means crystals have time to form, so the crystals are quite big. If the molten rock makes it all the way to the surface, it's called lava. Exposed to the air, it cools more quickly, so the crystals don't have much time to form, and as a result they're smaller. The fastest growing igneous rocks are those that emerge underwater. They solidify so quickly that crystals on the outside barely have time to form, and you're sometimes left with a rock as fine as glass, called obsidian. Although technically it is a rock, obsidian does look like a mineral, so it gets mineralogists very excited because there are simple people attracted to shiny objects. These types of formations are called pillow lavas, and they're very easy to spot. Here they are under the sea around Hawaii, and here are some the Earth made earlier. So if you come across an igneous rock on a romantic stroll through the countryside, you can now impress your girlfriend by explaining how deeply you think the rock might have cooled and solidified based on its grain size, and you can go through the various classifications of igneous rocks in some detail. And if you find yourself walking home alone, you'll understand why geology students don't have girlfriends. By the way, the name of the rock not only depends on the size of the minerals, but also the type of minerals. That's why most geologists always carry a hand lens along with the traditional hammer. One of my classmates was once asked by a lecturer what minerals were in one of the igneous rocks on a cliff face, and he said, "Don't know." The lecturer said, "Well, use your hand lens, man." After examining the rock for 10 seconds through the hand lens, the student gave his verdict. "Looks the same, only bigger." Ladies and gentlemen, this is the genius who would one day be entrusted with finding the oil that runs your car. Sometimes the molten lava contains a lot of gas, like steam and carbon dioxide, causing explosive eruptions. The lava is spat out so quickly it turns into ash and small rock bombs. This may not look like molten rock, but you can see it better at night in the same volcano. These layers build up into the familiar steep conical shape of what are called composite volcanoes. The ash hardens over time to form a rock called tuff. Hence the well-known expression, "It's tough at the top." When the lava is less gassy and explosive, as in Hawaii, it flows out along the landscape, making wider and flatter shield volcanoes. But most mountains aren't volcanoes, they're sedimentary rocks pushed up by tectonic forces, so that's what we'll look at in the rest of the video. To follow this process, let's start with the sedimentary material as it's moved around by currents and eventually falls to the seabed. As the environment changes over time, different materials, predominantly mud, silt, sand, calcium carbonate and bits of dead animals, are laid down one on top of the other. Over time, they harden, and that all has to do with pressure and cementation that I won't go into here. Since sections of crust are constantly moving, Eventually, the piece of crust these hardened sediments are riding on will collide with another piece of crust. If you want to know how crustal plates move and collide, see my last educational video, The Story of the Earth in 33 Minutes. So, what happens to the sedimentary layers? In this experiment, structural geologists, who don't like sleeping in tents, try to find out from the comfort of a warm, dry laboratory using layers of sand to represent rock strata. As one set of beds is pushed against the other, they're lifted up and begin to fold. As the pressure increases, the strata uplift and fold even more, sometimes to the point where the rocks that were underneath end up on top. These are called recumbent folds. And the purpose of recumbent folds is to confuse geology students who have to figure out why an older rock layer is lying on top of a younger one. Yes, that is me with all the hair. Being hairy is one of the entry requirements for a geology course, and when you graduate, you're given a beard. Even the women. Now, that's only a laboratory sand experiment. You might think, rocks don't behave like that in the real world. But yes, they do. The great thing about lab experiments, apart from being warm and dry, is that if you get the materials right, you can recreate what we see in the real world. Pressure can also uplift rock strata by faulting, in other words, creating huge cracks. Now that the rocks have been uplifted, whether by faulting or folding, the mountains have to be further shaped by weathering and erosion. As rain falls, water finds its way across the rising sedimentary beds and into the low points and cracks. As the mountains rise higher, the channels cut deeper and the cracks get wider. Now they're beginning to look like proper mountains. Contrary to popular belief, it's not just one tiny river that carves all this. These river channels expose the rock face, but then it's other weathering forces that do most of the work in opening them up. Same goes for rock formations that aren't folded or faulted, just pushed up intact, and as flat as they were formed on the seabed. Erosion eats away at minor cracks, which get larger and eventually become chasms that separate and isolate large chunks of rock, known as outliers. You can see them in the North American desert. Eventually, the rock gets eroded to a pile of sand blowing across the landscape. So how does weathering work? First, there's chemical weathering, such as dissolved carbon dioxide from the air mixing with water to make a weak acid. It dissolves the silicates and carbonates that make up most rock minerals. That's the weathering part. Then dissolved and broken rock is washed downwards, and the river carries them away. That's the erosion. Second, there's mechanical or physical weathering, like freeze and thaw, as water gets into cracks and crevices on the rock face. At night, or during the winter, every time temperatures dip below zero, the water freezes and expands, cracking the rock. More water then comes into the larger crack, and when that freezes, it expands, and the crack gets larger. Repeat this thousands of times, and the crack gets larger and larger until the rock cracks apart. Closer to the tops of mountains, the ice never melts throughout the year, so the ice acts as a kind of glue, keeping loose rock permanently together. But thanks to global warming, the ice that held the rock together for millions of years is beginning to melt during the summer. The rocks become unglued, and the result is dangerous landslides. A few years ago, I went to Switzerland to do a story on how this is affecting the Alps, and while I was interviewing a local expert on this phenomenon, we were interrupted by just such an event.
Maintenant, c'est plutôt partir du mois de décembre.
So the snow used to be around from around November to March, April. Now the snow doesn't begin until December, and we're just getting a rockfall here. The other side of the valley, these rocks are just crashing down into the valley below from where the glacier has been. I don't think there can be a better example of how the glue that has held these rocks together and held that mountain together is now coming apart, and the rocks are so loose they're just falling down.
En descendant, l'hiver.
The science of mapping this tangle of tilting and folding rocks is called stratigraphy. Apart from the traditional hammer, the only equipment a stratigrapher needs is a compass, a clinometer, and of course a carrot. Okay, I know what you're thinking. What the hell is a clinometer? Well, it's an instrument that measures the dipping angle of the rock strata. The hammer is there to expose fresh rock. And it's true, we do lick these rocks when we break them open. It makes it easier to see the grain structure and identify the rock. Of course, mineralogists do it because they like the taste. When I was a geology student, we used to studiously examine rock outcrops. Okay, this photo isn't showing that, but we used to studiously examine rock outcrops. We used to studiously examine rock outcrops. Look, this was a time when university education was free, so we didn't have any student loans to worry about. Oh, there it is. So, we used to studiously examine the outcrop by bashing it to pieces with our hammers. One day, the sedimentology lecturer admonished us. "Don't just go straight in there and start hammering at the rock," he said. "Stand back. Look at how the surface has been weathered. See if you can spot any cross-bedding, graded bedding, or unconformities. These are all clues." So the next day, when we got to an outcrop, we went in, and this time, we still started bashing it to pieces with our hammers, because the truth is, we just like bashing rocks. It's very satisfying when a layer of sediment that's been sitting untouched, since it was laid down 100 million years before dinosaurs came along, and in the space of half a second, is crushed under the hammer of an 18-year-old with acne. But with hindsight, our lecturer was right. I told you that on my first day I was mystified as to how flat beds on the seafloor turned into a chaotic jumble of rocks. But stand back, look closely, and there are clues. You can still see the traces of the flat beds where the sediment was laid down, even though the formation has been tilted and cracked. At the top of Mount Everest, too, you can still see the flat outline of the seabed, laid down 400 million years ago. Sometimes the clues are very obvious, but usually most folds and faults stretch for miles under our feet, so they can't be seen. This is what's underneath a 50-mile line across Greater London. It's the bottom of a fold, a syncline, which is why a river runs there, and the river is why London is there. It just goes to show how much our lives are influenced by geology, whether we know it or not. Stratigraphers need to build up a picture of what we can't see underneath our feet by looking at sparse and scattered outcrops that we can see. So they go off into the wilderness for months at a time, armed only with the essential tools they need to make their measurements: a hammer, a compass, a clinometer, and a carrot. What do you mean, what's a carrot for? They've got to eat. They leave behind unnecessary and cumbersome equipment like polarizing microscopes and thin section cutters, and a change of clothes, and deodorant. And when they come back to civilization, they're locked away in dark basements where they process all that information. From the various outcrops they visited, they plot the angle and direction of the dipping strata, and from that they build up a picture of what's underneath. The result is beautiful geological columns and cross-sectional maps like these. Stratigraphers are the medieval monks of the geology world, and not just because they're celibate for most of the year. Some rock types will baffle even the stratigraphers. The senior geologist I was working with in Australia told me about a stratigrapher who was out in the field and sent back some samples of what was obviously dunite with a note. "Can you tell me what the pretty green rock is?" The people who are experts at identifying rocks are called petrologists, from the ancient Greek word petros, rock, the same word that gives us petroleum, rock oil. Now, I have to tell you, these people are fun. Just take a look at this hysterical joke from a petrology website, and you'll see what I mean. Okay, not all their jokes are as funny as that one, but what they lack in quality, they make up for in quantity. The reason petrologists have time to think of all these jokes is because they spend long hours looking at rocks, and then more rocks, and then other rocks. So they don't waste time doing the kind of frivolous things normal people do, like going out. Anyway, let's get back to weathering. There's a phenomenon called differential weathering, which means rocks weather at different rates. You can see here the hard layers are protruding because the softer layers on top and below have been weathered more quickly. And the material is different because, of course, the environment in which they were laid down changed over time. When hard and soft layers are tilted, the same process can form hills. Even two layers of the same rock type can have different hardnesses. So the softer layer will erode faster, and when it's underneath the harder layer, that can leave us with features like these. Igneous rocks are the hardest of the lot. Remember that pool of magma I showed you earlier? Well, it cools and solidifies into a hard, large-grained igneous rock, usually granite. So when the softer rocks around it are eroded, the granite remains, a prominent feature of the landscape called a massif. Now, weathering patterns in one type of rock are so distinctive that even geology students can spot it from a distance. This is limestone, calcium carbonate, the stuff seashells are made of. And calcium carbonate is a strong alkali, so even a weak acid like CO2 dissolved in water will eat it away very quickly. This is a model, but it shows how limestone has a tendency to crack, not only along its bedding planes, but also at right angles to them, forming blocks. So it's like the sandstone outlier process we saw earlier, but on steroids. Acidic water seeps into cracks and dissolves them, isolating and reducing the blocks. It forms what's called a karst landscape. The limestone also gets eaten away underground, causing huge caves, which sometimes flood when the water table rises. When these can no longer support the weight of rock above them, they collapse, forming sinkholes, like the famous cenotes of Mexico. Because it's fine-grained and often made from fossilized sea creatures, limestone can be a treasure trove of fossils, a branch of geology called paleontology. Here we see a fashionable paleontologist in his typical working attire, just off on a jaunt collecting fossils. You can look for fossils yourselves, but it's not a good idea to take a paleontologist with you because when they find something interesting, they tend to drool. Finally, there's one last process shaping our mountains, and it's the most recent. Over the last 2 million years, the Earth has been, and still is, in an ice age. During colder phases, called glaciations, ice sheets and glaciers advanced over much of the continents, and as they moved, they shaped the ground underneath. Think of a glacier as a slow-moving river of ice. Rocks that had shattered through freeze-thaw fell into the glaciers. Rocks that were plucked from the ground were swept along, and all were smoothed over thousands of years as they rubbed up against other rocks. They were dragged across in situ formations, leaving scrape marks we can still see today, called glacial scarring. V-shaped valleys were ground into U-shaped valleys by the rivers of ice. When the ice finally melted and the glaciers retreated, the huge boulders they'd carried were left high and dry, dumped on the landscape. They're called erratics. Now, how can you tell the difference between a balancing rock that's an erratic from one that's been weathered, an outlier? Obviously, the outlier is still attached at the base because it hasn't been moved. It's in situ. But there are other clues. Strata in a weathered rock will typically have the same dip and direction as the strata to which it's attached, and it'll fit into the sequence. A glacial erratic is usually smoothed and made of a completely different material to the rock it sits on, unattached. You can see the strata quite clearly in the famous balanced rock of Colorado Springs. It was formed nearly 300 million years ago from sand deposited at sea, then lifted up with the Colorado mountains and weathered over millions of years by wind and rain. To get to this unique site involves a long hike through the eastern Rocky Mountains. At least it would, except this is the United States, so of course they made it into a drive-in. So the growth of mountains is a tug-of-war between uplift and erosion, the two great principles of geology. As the continents continue to collide today, uplift in these regions is greater than erosion, so mountain chains between them are still rising. Africa is still crashing into Europe, squeezing the Mediterranean and throwing up the Alps. India is still crashing into Asia and lifting the Himalayas. The higher these mountain chains go, the faster they weather. Where the collisions have stopped, the forces pushing these mountain ranges up are no longer operating, so erosion takes over as the dominant force. The longer the period of tectonic inactivity has been, the lower the mountains have been worn down. The Grampian Mountains in Scotland, for example, formed when North America crashed into Europe 450 million years ago, and they were once as impressive as the Alps. Then the collision stopped, erosion took over as the dominant force, and most of the sedimentary rock has now been eroded away. All that's left are the igneous and metamorphic rocks that were once deep inside the mountain range. If you're a geomorphologist, I bet you're getting very excited right now. If you think I've left a few things out from a 3-year geology course in a 30-minute video, you'd be absolutely right. I've left out about 2,624.5 hours of material, so I'm sure the comments section will be filled with things I supposedly forgot to mention. Thanks in advance, but I haven't forgotten anything. I've just shown you a rough guide to the basics. If I've got anything wrong, and you're watching this more than 2 days after the video was released, it will already be in the corrections section of the video description. So do check that, please. And if you'd like to find out more, well, there's a wealth of information on the internet, from online encyclopedias to universities, schools, and geological institutes with educational websites. And all for free. You don't know how lucky you are to have all this information with just a few clicks of a search engine, because when I was a student, we had to scour the library to find what we needed. So, of course, in the internet age, everyone is now learning from these sites and is better educated. Who am I kidding? Of course they aren't. People don't want to bother using the internet to find out how the Earth really works. It's much more exciting to take lessons from bloggers and vloggers who say that the Earth is expanding, or it's hollow, or it's flat, rather than trying to understand any of that complicated math, chemistry, and geophysics that real geologists have to put up with. It's so much easier to imagine that a balancing rock on Mars was carved by Martians, and to save you the trouble of learning why a piece of coral is found on top of a mountain, it's much easier to put the question on Reddit and have people explain to you maybe someone carried it there. To those people I say, by all means ignore the discoveries made by petrologists, mineralogists, stratigraphers and paleontologists who cut themselves off from the civilized world for most of the year and forego the comforts of life, like bathing, in order to find the oil that runs your car, the coal that powers your electricity, the iron ore that builds the bridges you drive over, and the precious metals you need for your phone. Ignore their work and their sacrifice if you prefer to believe in Martians. But if you don't believe any of this geology stuff, then stop running your car, your computer, and your phone and don't go anywhere. See what life would be like without them. To the others who've made it this far and who are interested in the real world, I hope this video has been useful. Wait, don't go yet. I don't ask for contributions for my channel, and I don't make any money out of my videos, so if you like the video and want to contribute something, I always request that you send the money to this charity instead. It's an innovative scheme that offers subsidized medical care to poor people who live in or near forests in exchange for not cutting down the trees. Because the reason they cut down the trees in the past was because they needed cash urgently when members of the family were sick. The scheme has been so successful that studies have been written about it and found that people in the areas where it's operating are healthier and illegal logging has been drastically reduced. So far, donations in my name from subscribers to this channel have reached $270,000, and that's helped expand the scheme from Indonesia to Madagascar and Brazil. So if you've always faced the dilemma of whether you should donate money to help poor people or save the forests, well, now you can do both. Details are in the video description.